In this video, we are going to study permutation without replacement with some identical items, and we are going to derive this formula in different ways. So let's start with a question. Find the number of 5-letter words that can be formed using the letters of the word A, B, C, D, E. So this word has 5 letters, and we can create different words by changing the order of these letters here, such as the word C, A, B, D, E. And in this case we notice that letters do not repeat in this word, so we have here no replacement. If letters repeat in a word such as C, C, A, B, then in such case we have replacement. But in our case, we don't have any replacement. And the second thing is, order of letters is important. So we are changing the order of these letters to change the word. We are going to create all possible ordered words using the tree diagram according to the following rules. The first one, we are withdrawing these letters in 5 consecutive turns. And why 5? Because if we want to create a 2-letter word, we have to withdraw twice. If we want to create 5-letter words, then we have to withdraw these letters 5 times. So here we have 5 consecutive turns of withdrawal. The second rule, after each withdrawal, we do not return the letter to the urn. So here we have the case of no replacement. We do not want any letter to be repeated, just we want to change the order. And the third one, we write the withdrawn letter in order. After we finish all the possibilities, we write these letters in order. We have to respect the order here. So in the first row, we may pick up A, B, C, D, or E. So we have 5 letters to pick up. But in the second row, we have less letters to pick up, such as B, C, D, and E. So if we pick up letter A, we are left with the remaining 4 letters. If we pick up letter B, we are left with the remaining 4 letters. And now the third row. So we already picked up A and B, so the remaining letters are C, D, and E. And in the fourth row, we have only 2 letters remaining, and in the fifth, we have only 1 letter remaining. After finishing all the draws, we can write all possible result or all possible ordered words using the exact order of the draws we have made. So let's say here we have C, A, B, D, and E, and this is going to be C, A, B, D, and E here. So we generated this possible ordered word, and this tree diagram now is showing all possible ordered words. So we are going to see them here in more clarity. We draw the subtrees of A, for example, and we can see here that if we draw A first and C second and D third and B fourth and E fifth, we generated the ordered word A, C, D, B, and E. And so the same thing apply for the other subtrees, subtree of B and C and D. And we do not forget the subtree diagram of letter E also. So going back to the old tree diagram here, we have all possible ordered words, and now we have to count them. So for each subtree, we have 4 times 3 times 2 times 1 possible outcome for each subtree. And for all the subtrees, we add them together and we get 5 times 4 times 3 times 2 times 1, which is 5 factorial, and this is equal to 120. So we have here 120 different ordered words that can be generated out of these 5 letters. We could have used the formula of permutation without replacement of n objects taken n at a time from the beginning, but we preferred to use the tree to generate all these ordered words because we are going to reuse it again later. So in such case we have 5 letters, we are permuting 5 letters, and we are going to permute 5 letters taken 5 at a time, and that is 5 factorial. So here we have permutation without replacement of 5 different ordered letters taken 5 at a time, and that is equal to 120. And now we ask a question about creating a word with identical letters, and that is find the number of 5-letter words that can be formed using the letter of the word A, B, O, O, O. So now we have in the urn these 5 balls with the 3 O's and 2 letters A, B, and we notice that the word A, B, O, O, O contain 2 distinct non-redundant letters, and they are A, B, and 3 identical letters, and they are the 3 O's here. So we define the letters over the list. And why do you define these letters over the list? And the reason is the list can contain letters that are identicals. A set cannot have such characteristic. So here we define a list as ordered symbols, element, or objects that can be redundant, such as this list here, which contain A, B, and 3C and 2D. Now, what could this new ordered word be like? It could be like O, B, O, A, O, or O, O, B, A, O. So again, we are withdrawing without replacement. So A is only repeated once, and B is repeated only once, and the 3 letters cannot be repeated more than 3 times. They are repeated only 3 times. So we have here letter should not be repeated, so it is the case of no replacement, and order of letters is important. So OB is different than BO, and for this word here, which contain A, B, C, D, and E, we are going to map the letter C into the letter O, and the letter D into O, and the letter E into the letter O. And now this word here, A, B, C, D, E, is mapped into the word A, B with the 3 O's. Now, in order to create the tree diagram which generate all possible ordered words of the letter A, B, and 3 O's, we have to replace every C, D, and E with the letter O. So we are going to map that. So we map these 3 letters into O, and we replace every C, D, and E in the old tree with the letter O. And now we notice that this tree has been generated, but we have one issue with it. There are similar ordered words in it, and we need to cancel this similarity. So let's have a close look at the subtree A. So we have here A, B, and 3 O's here repeated 6 times. So in such case, we have to cancel these 5 words here to have only one ordered word. And we have to repeat that for the rest of the subtrees, B and O, and the second one O, and the third O here. So now going back to the mother tree here, we are going to discount any similarity in ordered words, and we end up with with these words here. So let's have a close look at them. So we have subtree A, and we have only four distinct words here in order, and for subtree B also we have 4, and for the subtree O we have 12 different ordered words. And now going back to the old tree, we have this tree generating all kind of different ordered words out of the letter A, B and 3 O's. We need to count them, so we have 4 in this subtree and 4 and 12 in the O subtree. We add them together and we get 20 different ordered words that can be generated out of the list A, B and 3 O's here. So now what is the relation between the number of words generated out of 5 different letters, which is 120, and the number of words generated out of 5 letters, but 3 of them are identical, and that is 20. So we realize that 120 divided by 6 is equal to 20, but 120 is 5 factorial and 6 is 3 factorial. So now we have 20 equal to 5 factorial divided by 3 factorial. Now we write them in different colors here, and we write permutation of 5 objects, semicolon, 3 of them are identical, equal to the number of object factorial divided by the 3 identical object factorial. So n is equal to 5, and a is the number of identical objects, which is 3, and now this relation can be written as p in a equal to n factorial divided by a factorial. So this is the relation we are seeking. Another way of deriving the formula of permutation with identical objects, we can imagine that we have 5 empty cells for 5 letters, and that letter A can occupy one of these empty cells in 5 ways. So let's say that letter A is occupying the first cell, and so letter B can occupy the rest of these empty cells in 4 ways. So let's say B is occupying the second cell. We need to realize that empty cell need not be chosen because they are by definition empty cells, and for each location of A and B we are going to get a new word. So if we change the location of A and B, we are going and we map empty cell into the letter O, we are going to get this word, for example, A, B and 3 empty cell, which is 3 O's here, or O, B, A and 2 O's, and etc. So we can conclude that for each location of A and B we have a new ordered word with 3 identical letters. So now we conclude the following: that number of way of choosing the letter A, B in the 5 empty cells is equal to the number of 5 letter words that can be formed using the letter of the word A, B with 3 O's. So according to the multiplication principle, the number of ways of choosing the letters A, B in the 5 empty cells is 5 times 4. And 5 times 4 can be written as a fraction. We multiply the numerator with 3 factorial and the denominator with 3 factorial, and we get 5 factorial divided by 3 factorial, which is the number of words that can be generated out of the word A, B with 3 O's. So we arrive at the same formula we found before, which is permutation of 5 objects, 3 of them are identical, equal to the number of object factorial divided by the number of identical object factorial. If we need solid proof for the general formula of permutation with identical objects, we can do the following. So let's assume we have the word A, B, O1, O2, O3 with all distinct letters. We know that we can generate 120 words ordered out of these 5 different letters. Now we are going to fix A, B and permute these 3 letters in the underneath tables. So here we fix A, B in the first and second column, and then we shift them again and again and again. But in each table, this O1 and O2 and O3 can be permuted in 6 different ways, which is 3 factorial. Now, how many words each table has? We can see that we have 1, 2, 3, 4, 5, 6, because we have 6 factorial resulting from permuting O1, O2, and O3. However, AB can be permuted in 2 different ways. We can write AB or BA. So AB can be permuted in 2 factorial ways, and O1, O2, O3 can be permuted in 3 factorial ways. So words in each table can be permuted in 2 factorial times 3 factorial ways according to the multiplication principle. So each table contains 6 times 2, 12 different words. And for 4 tables, the number of words that can be generated is 4 tables times 2 factorials times 3 factorials. Now for all possible location of O space B, we have the following permutation. So we have here 3 tables, and the number of words that can be generated following the previous judgment is going to be 3 tables times 2 factorials times 3 factorials. Again, for all possible location of A space B, we have only 2 tables, and the number of words that can be generated in this case is 2 tables times 2 factorials times 3 factorials. And for the final location of A and B, which is A with 3 empty space B, we have only 1 table, and the number of permutation generated in such case is 1 table times 2 factorials times 3 factorials. Now the number of words that can be generated out of all possible location of A and B is the sum of all these previous numbers, and is going to be 120, which is 5 factorial. Now let us map the 3 different letters O1, O2, O3 into the letter O. As we see, in this case, each table with different words will be mapped into a table with the same word. So each table will be divided by 3 factorial, which is the number of permutation of O1, O2, and O3. So we say when we count the number of words in each table after mapping, they will be divided by 3 factorial. Hence, we have to divide the total number of words before mapping with 3 factorial to get the number of words after mapping. So since the total number of words after mapping is equal the number of permutation of the word AB with 3O, in such case the number of permutation of this 5-letter word with the 3 identical items is going to be equal to this 220 divided by 3 factorial, which is 5 factorial divided by 3 factorial. Now let us generalize this formula. Let's assume we have this word AB with 3 identical O's and 4 different Z. We realize that the number of objects is 9 and the number of permutation of this word with 3 identical O's is going to be 9 factorial, which is the number of objects, divided by 3 factorial, which is the number of identical letters. So now, for each location of these letters here in this word, such as this word here or this word here, where we change the location of A, B and the 3 O's, we have how many permutation for this? For that we have 4 factorial permutation. But the sum of all these permutation is 9 factorial divided by 3 factorial. Now if we map this word which contains 4 different Z into a word which contains 4 similar Z, the number of permutation of the word with similar Z is equal to the number of permutation of the word with different Z divided by 4 factorial, as we did before exactly. Why? Because for each location of these letters here, we have 4 factorial permutation of the letter Z. So if we make all these Z similar to each other, we have to divide every table over 4 factorial. So in such case, the number of permutation of this word here is going to be 9 factorial divided by 3 factorial, and all of them divided by 4 factorial. In other words, it's the number of permutation of this word with 4 different Z divided by the permutation of these 4 Z, and in such case we get the number of permutation of this word with 4 similar Z. And we can write permutation of 9 objects with 3 and 4 identical items is equal to 9 factorial divided by 3 factorial times 4 factorial. Let us now draw the following conclusion. If we have n objects containing x distinct non-redundant objects, a alike objects of one kind, b alike object of a second kind, and c alike object of the third kind, defined over this list here, where x is the number of distinct non-redundant objects, and they are t, u, v, and w, and a is the number of a identical object here, b is the number of b identical object here, and c is the number of c identical objects, provided that n is equal to the sum of all of them. So n is the total number of objects and is equal to the sequence size, and n is equal to the sum of all these identical and non-identical objects. So in such case, the permutation of n objects taken n at a time with a identical objects, b identical object, and c identical objects is equal to the number of objects factorial divided by the multiplication of the number of identical objects times the number of the other identical objects times the number of the other identical object, and so on. Now we need to read this formula precisely. So P is permutation of ordered objects taken n at a time, and here we have to put semicolon, and if we don't write anything here it means without replacement, with A identical object, B identical object, and C identical object. So we can read it as permutation without replacement of n objects taken n at a time with A identical objects, B identical object, and C identical objects. And this is going to be a very precise reading of it. Now, what are the conditions to apply this permutation formula? We have the first condition, order of objects is important. And the second one, no replacement of objects. And the third, we generate a sequence of size n, no more and no less. We cannot generate a sequence of size n plus 1 or n minus 5, etc. So that means generated sequence size is equal to the number of objects in the list. And now we are going to know the characteristics of the generated sequence. The first one is the sequence size is n. So the sequence has n objects, no more, no less. And the second, objects that are distinct and non-redundant, such as T, U, V, and W we have seen before, do not repeat in the generated sequence more than once. And for identical objects such as A, they repeat A times, and identical elements such as B, they repeat B times, and C repeat C times. So we have a question here. Find the number of 15 letter words that can be formed using the letters of the word T, U, V, W, 3 A's, 2 B, and 6 C's. The first thing we do, we write the list of these letters, and we find the number of non-redundant letters and the number of identical letters. We add them together and we get n equal to 15. So we are forming 15 letter words, and we are having here 15 objects. If the question is asking form 20 letter words out of these 15 objects, then we are going to have totally different formula, not the formula we have in this video. So we apply the permutation formula, and we substitute N, A, B, and C, and we read it as follows. Permutation without replacement of 15 letters, taken 15 letters at a time, with 3 identical letters and 2 identical letters and 6 identical letters equal to 15 factorial, divided by the number of the first set of identical letter factorial times the number of the second set of identical letter factorials times the number of the third set identical letters factorial. And we get 151,351,215 letter ordered words that can be formed using the letter of the word here, 2, U, V, W, etc. In the generated words, each word size is 15, and the letters in these words that are distinct and non-redundant, they do not repeat more than once, and the 3 identical letters repeat 3 times, the 2 identical letters repeat twice, and the 6 identical letters repeat 6 times. So let's have a look. We may have this word here, and again we may generate different ordered words, but the the T and U and V and W are not going to be repeated more than once, while the identical letters such as BB are going always to be repeated twice, and the identical letters such as A are going to be repeated all the time 3 times, and the repeated letters such as C are going always to be repeated 6 times. Thank you for watching and have a good day.